All right, you are welcome again. Today, let's continue our series on Laplace transform, okay? And then we are considering the Laplace transform of elementary functions. In part 1, we talk about the introduction and some other things. But in this part now, we are going to continue. In number 8, we have the function f of t is equal to tn for n is equal to 1, 2, 3, and so forth. So now, how can we find the Laplace transform of this function f of t equal to t raised to power n? I want you to pay attention to this. It's very simple. We can do it together, okay? Now let's go. Our function is t raised to power n. Okay, so when we say the Laplace transform of f of t, we are saying the Laplace transform of t raised to power n. Now, going with the definition of Laplace transform, you will recall that Laplace transform of f of t is equal to the integral from 0 to infinity e raised to the power of minus st f of t dt. That is the Laplace transform of f of t. So now, our f of t is t raised to power n. So when we say the Laplace transform of t raised to the power of n, we are talking about the integral from 0 to infinity e raised to the power of minus st. In place of f of t now, we replace it with t raised to power n. Then we have dt. Okay, good. Now, before we go further, I want to introduce something to you. We call this the gamma function. What is the gamma function? Look at the sign. When we say the gamma of n, look at the sign. The gamma of n. What is it talking about? You say it is the integral from 0 to infinity x raised to the power of n minus 1 multiplied by e raised to the power of minus x dx. Hello. When we say gamma function, and then you say gamma of n, it's talking about the integral from 0 to infinity x raised to the power of n minus 1 multiplied by e raised to the power of minus x dx. Please, we call this the gamma function. I want to introduce this to you. You are going to use it in a nearby future. Okay, now let's go. We have our function, the integral from 0 to infinity e raised to the power of minus st multiplied by t raised to the power of n dt. How can we evaluate this? Please pay attention. Let's go there. Now, this place we have minus st. Let's call this st a letter. We want to evaluate this integral. Now, we say let's call this st a letter. Let's use letter x. So here, we say st is equal to x. Let st equal to x. In this, our function, the integral from 0 to infinity e raised to the power of minus st t raised to the power of n dt. Anyway we see st, let's replace it with x. We want to evaluate the integral. Okay, good. Now, s is a constant, t is a variable, and x is a variable. Okay, good. So in this case now, we want to change st to what? To x. So here, since t and x are all variable, we can differentiate this function either with respect to t or with respect to x. Whichever one, they are going to give you the same thing with what we are going to do. Okay, good. Now, let's do them in the separately. We differentiate with respect to t and we differentiate with respect to x. Now, differentiating with respect to x. Now, first, what do we do? When you differentiate st with respect to x, remember s is a constant and t is a variable. Now, we want to differentiate this st with respect to x. Okay, with respect to what? To x. So we take s one side. Now, differentiating t with respect to x is going to give you the t all over the x. Now, multiply by the s now. That means we are going to have s, the t all over the x. I'm very sure you can still record this, right? Good. Now, equal to, going to the other side, we have x. Differentiating x with respect to x is going to give you 1. Okay? Now, look at this. In this integral, we are trying to evaluate, and we want to change the variable t to x. So, here that we have the t is no longer going to be dt, because the variable t have changed. So we want to find a new value for dt. So in this place where we have s dt all over the x is equal to 1. Let's try and see if we can make dt the subject, so that as the variable t have changed, then the t will also change. You get this, right? Good. So now in this case now, we have x dt all over dx. First of all, we multiply both sides by dx, or you say you cross multiply. Either you multiply both sides by dx or you cross multiply. So when you cross multiply, we are going to have s dt is equal to dx. S dt is equal to dx. Now, probably making the t the subject now, that means we strive out this s by dividing both sides by s. So when you divide both sides by x, you are going to have the t is equal to dx all over s. So when you divide both sides, we have s dt all over s is equal to dx all over s. So therefore, we have dt is equal to dx all over s. Is it true? Yes. So now we have succeeded in making the t the subject. Now, I told you can also differentiate with respect to t, because both of them are variables. X and t are variables. So you can differentiate to either of them. Okay? Now let's go. Differentiating st equal to x with respect to t. What are we going to have? Now, when you differentiate st with respect to t, what will you have? We are going to have s. Okay? Yes, you recall that s is a constant and t is a variable. So now differentiating st with respect to t is going to give you s. All right? Good. Now, differentiating x with respect to t is going to give you dx all over dt, telling you that this x is now in a derivative form, dx all over dt. Is that clear? Good. And then you remember that we are changing the variable t to x, so there is a need for the t to also change. So what are we going to have as a new value for dt? That means we make dt the subject here. For us to do that, let's first of all cross multiply. When you cross multiply, in this place we have s is equal to dx all over dt. What do we have? We are going to have s dt is equal to dx. All right. Now divide both sides by s. We are going to have dt is equal to dx all over s. All right. Good. Now let's go. We differentiated st is equal to x with respect to x and with respect to t, and then make the t the subject. We have the same value, and then we say that dt is equal to dx all over s. Is that clear? Good. Now let's go. In this place, we say let minus st be called the letter x. The key point I want you to take is that we want to change the variable t. Okay, so now as we want to change the variable t, what are we going to replace t with? We say st to be called the letter x. Now what are we going to write in the place of t itself? That means we have st is equal to x. We make t the subject so that we can replace t with the equivalent value. Okay, so in this place we say st is equal to x. Now we divide both sides by s so that we make t the subject. So when you do so, we are going to say that t is equal to x all over s. Is it true? Yes. Now we have succeeded in getting a new value for the t, and then a new value for t, and then a new value for st. Is it true? Yes. Now let's go again. We have changed the variable t to x. Now also the limit from 0 to infinity will also change. Okay? But let's not conclude first. Let's see the new value. First of all, we say as t approaches 0, that is the lower limit. Okay? We have the boundary, upper bound, lower bound. Okay? Or we say the limit. So as t approaches 0, what will happen to the new value x now? So look at it. We have st is equal to x, right? Good. As t in this st approaches 0, if this t turns to 0 now, what will happen? Multiply by s, it will give you 0. Okay, so 0 is equal to x. So for it to be the same, that means x is equal to 0. Hello? That means x is equal to what? 0. You see? So as t approaches 0, t now is 0. Multiply by s, it gives you what? 0. That means you say that x is equal to 0. As t approaches 0, x will also approach 0. Also, as t approaches infinity, what will happen? As t approaches infinity, what will happen? Here we have st is equal to x. So if t is now infinity, what will happen? This infinity multiplied by s, what will it give you? It will give you infinity. That means we say that x is equal to infinity. Say that x is equal to infinity. So here we say that the upper bound, as t approaches infinity, x will also approach infinity. Then the lower bound, as t approaches 0, x will also approach 0. Is that clear? Good. Now let's go. The integral that we want to evaluate is this. The integral from 0 to infinity, e raised to the power of minus st, t raised to the power of n, dt. Okay? And then we say, let st be called the letter x. Let's replace it. We have the integral, the lower bound and the upper bound, they are the same, right? Good. That means we say the integral from 0 to infinity, e raised to the power of minus. In place of st now, we write what? X. Okay? Good. Let's go. And then we make, in this st is equal to x, we make t the subject, and we obtain that t is equal to x all over s. So in place of this t, we can write x all over s in bracket raised to the power of n. Okay, good. Multiply by, when we differentiated either with respect to t or with respect to x, and we make dt the subject, we obtained that dt is equal to dx all over s. So in place of dt, we write what? Dx all over s. Let's go. In this center term where we have x all over s raised to the power of n, let's open the bracket applying the law of indices, what do we have? We are going to have the integral from 0 to infinity e raised to the power of minus x. This n we distribute to the numerator and to the denominator. That means we are going to have x raised to the power of n all over s raised to the power of n. Multiply by, here we have dx all over s. Is the same thing as saying 1 all over s multiply by dx. Hello? It's the same thing as saying 1 all over s multiply by dx. Alright? Good. Now let's go. Here we can also bring down this x raised to the power of n. So when you separate it, that means it's still the same expression as saying the integral from 0 to infinity e raised to the power of minus x. Okay? When you say s raised to the power of n multiply by s, applying the law of indices is going to add their what? Their exponent, their power. Going to add their power. Okay? So that means when you say s raised to the power of n times s is going to give you s raised to the power of n plus 1. Is it true? Then we have the x. So we can bring down x raised to the power of n. Okay? So when you bring it down, we can have something like this. The integral from 0 to infinity e raised to the power of minus x 1 all over s raised to the power of n plus 1 multiplied by x raised to the power of n dx. Do you get this? Yes. Now, carefully looking at this, what do we say that is our new variable now? Our new variable is what? Is x. So any value here that is not having x, we call it a constant. We call it a what? A constant. And then in integration, any constant, we take it behind the integral sign. So carefully looking at this, you see that 1 all over s raised to the power of n plus 1 is a constant. There is no variable x on it. Now we take it behind the integral sign. So we are going to have 1 all over s raised to the power of n plus 1. The integral from 0 to infinity x raised to the power of n multiplied by e raised to the power of minus x dx. Hello? Do you get this? Yes. So this is where we are now. Please pay attention. From the beginning, I introduced something to you. What did I call that? Gamma function. Yeah, I introduced a gamma function. Okay, so now, and then we said, let's bring it back again. We said that the gamma function, let's say gamma of n. The gamma of n is the same as saying the integral from 0 to infinity e raised to the power of n minus 1 multiplied by e raised to the power of minus x dx. Is that true? Yes. Now let me show you something. What if you say from this gamma of n now, what if you say gamma of n plus 1? What will it be? Gamma of n plus 1. So that is anywhere you see n in this integral, we replace it with n plus 1. Okay, that is just the same thing. Okay, so when you say the gamma of n plus 1, it's going to be the integral from 0 to infinity x raised to the power of, in this place we have n, we say n plus 1 in bracket minus 1. Then multiply by e raised to the power of minus x dx. Hello. Now let's go. In this power now, where we say n plus 1 in bracket minus 1. So when you remove the bracket, we're going to have n plus 1 minus 1. So 1 minus 1 is what? Is 0. So we will only have n remaining. Okay, so now we simply say that the gamma of n plus 1 is the integral from 0 to infinity x raised to the power of n multiplied by e raised to the power of minus x dx. Hello? Okay, hope you are following. So here we see the gamma of n, we see the expression, and then we try to say what of n plus 1. So in the integral, anywhere we see n, we replace it with what? N plus 1. So that is, we want to find the gamma of n. Alright, good. Now let's go again. Gamma function in terms of factorial, what is it? Hello. What we just did now is gamma function in terms of integral. Okay, now let's go. The gamma function in terms of factorial, what is gamma of n? Now we can say that gamma of n in factorial is n minus 1 in bracket factorial. Is the same as the gamma of n. Okay, the gamma function. So when you say the gamma of n is the same as n minus 1 in bracket factorial. Okay, so and then we just solved for n plus 1. What if you say n plus 1 also in terms of factorial again? So anywhere in this factorial, anywhere we see n, we replace it with what? N plus 1 also. Okay, so now let's go. When we say the gamma of n plus 1 is equal to, in place of n, we have n plus 1 in bracket minus 1, all in bracket factorial. So let's open the inner bracket. So when you open the inner bracket, we're going to see that n plus 1 minus 1. So 1 minus 1 is going to give you 0. So we only have n remaining. So here we see that the gamma of n plus 1 in terms of factorial is n factorial. Is what? Is n factorial. Now look at this. This n, the gamma of n plus 1 is the same thing as the integral that we solved and we obtained. Hello. We solved. We will try to solve our integral, and then look at where we arrived. We arrived at 1 all over s raised to the power of n plus 1, the integral from 0 to infinity, x raised to the power of n, e raised to the power of minus x dx. Right? Good. And then we say, what is the value for the gamma function of n plus 1? So we say that the gamma function of n plus 1 is the integral from 0 to infinity, x raised to the power of n multiplied by e raised to the power of minus x dx. Hello. So now again we say, what is the value of the gamma function of n plus 1 in terms of factorial? And then we say that is the same as saying n factorial. Hello. So now look at this now. So in this place we have 1 all over s n plus 1, the integral from 0 to infinity, x raised to the power of n multiplied by e raised to the power of minus x dx. Okay, here we say that this integral from 0 to infinity, x raised to the power of n multiplied by e raised to the power of minus x dx is the same as the gamma function of n plus 1. Is the same as the gamma of what? N plus 1. Okay, good. Again, let's multiply these two together now. That means we are going to have the gamma function of n plus 1 all over s raised to the power of n plus 1. Okay? The gamma function n plus 1 all over x raised to the power of n plus 1. And then we say the gamma of n plus 1 is the same as what? N factorial. Isn't it? So that means we can replace gamma of n plus 1 with what? N factorial. So when we do so, we are going to have n factorial all over Sn plus 1. All right? Good. So therefore, we have just simplified, evaluated, and computed. And we see that the Laplace transform of t raised to the power of n is equal to n factorial all over s raised to the power of n plus 1. Very sharp, very simple, and very easy. We just explained how to go about it step by step until you discover that the Laplace transform of t raised to the power of n is equal to n factorial all over Sn plus 1. Hello. All right, let's go. We are talking about the Laplace transform of elementary functions, and we just treated one of them. Let's go to number 9, the next one.